Okay, and I believe your chart does have those changes in angles. They say that it's going to be less than those specific numbers, which will help you see that, visualize that from that chart, because you have that chart on your tests. Okay, so make sure you utilize that. Okay, so we've been talking about all of these molecules with a central atom, but we know that in our natural world, not every molecule has one atom in the center with 4 atoms coming off of it. Okay, it's never that simple. So we need to talk about our molecular shapes when we have molecules with multiple central atoms. So when I have 2 or more central atoms, how do we determine the shape of those central atoms? So, the geometry of more complex molecules can be determined by treating them as though they have multiple central atoms. So here I have an example where I have 2 central atoms, one being a carbon and one being an oxygen. What we're going to do is just treat those as if they're their own central atom. So if we look at the carbon, I have my electron domains going in 1, 2, 3, 4 directions. It doesn't matter that when I go this direction, that oxygen has something coming off of it, because that hydrogen is not touching that carbon. They don't touch each other, therefore it doesn't count towards its electron domains. Okay? It doesn't matter that that oxygen has 2 lone pairs coming off of it, because those lone pairs are on the oxygen, not on the carbon. So, we still look at the number of electron domains. This is where thinking about them as directions is useful. So if my electrons are going in 4 different directions, it just doesn't matter what comes after the next atom. It doesn't matter that that oxygen is bound to a hydrogen. It doesn't matter that that oxygen has lone pairs on it. It does not matter, okay? So if I treat this carbon as its own central atom, it has 4 electron domains, meaning its electron domain geometry is a tetrahedral, and the molecular geometry is also tetrahedral, because there is no lone pairs on the central atom. Now, if we look at the oxygen and treat it as its own central atom, well, I have electrons going in 1, 2, 3, 4 directions. Again, it doesn't matter that when I go this way, this carbon is attached to 4 hydrogens. Those hydrogens are not touching that oxygen in any way. So they're not considered as being a part of that oxygen's geometry. Okay? So it doesn't matter that that carbon has anything coming off of it. We just want to look at the way the electrons are going. And in this case, it's 4 different directions, 2 of which are in bonds, 2 of which are in lone pairs. So my electron domain geometry is for 4 electron domains, which is tetrahedral. My molecular geometry is now 2 bonds, 2 lone pairs. So that would be a bent geometry. Okay, so that oxygen has a bent geometry. That carbon has a tetrahedral geometry. It does not matter that they are attached to each other. Okay? So, let's keep practicing that. Let's determine the electron domain geometry of the labeled carbon in aspartic acid. So let's look at this carbon here. Determine the electron domain geometry of that carbon. Now the first thing you're going to want to do is check your octets. When you're given a structure, check your octets. We know carbon won't have an expanded octet, so we're looking for it to have 8 electrons around it. Well, it has 1, 2, 3, 4 bonds. Each bond has 2 electrons, so it has 8 bonds total, or 8 electrons total. So we have an octet around that carbon. Because what we'll find on some of these structures is they don't show their lone pairs. So let's look at this oxygen here, for example. The oxygen has 1, 2 bonds, which would only be 4 electrons. Obviously, we're not going to have a structure that doesn't obey the octet rule, so we'd have to infer that there are 2 sets of lone pairs on that oxygen. Okay, so even though we're not drawing the Lewis structure here, if it's given to us, we just want to double check our octets. So let's get back to the question at hand, though. what is the electron domain geometry around this carbon? So it doesn't need any lone pairs. We said that it has 2 single bonds and a double bond. So determine the electron domain geometry of that carbon. If it has 3 electron domains, then it would be trigonal planar. Okay, and if we were talking about the molecular geometry, it would also be trigonal planar because there are no lone pairs. Okay, let's keep on going. Okay, for this molecule, we want to describe the geometry of each central atom. Now I'll label these for you. This is oxygen, this is carbon, this is carbon, this is nitrogen, and these white guys are hydrogens. Okay, so the first thing we want to do is check our octets. Since we're going to be describing the geometry of each central atom, okay, the oxygen, the 2 carbons, and the nitrogen, okay, we want to just double check that we have all of our octets complete so we know our lone pairs. So pause your video and put your lone pairs on these atoms so that they complete their octets. Some may not need octet or lone pairs, some may. They may need 1, they may need 2. Okay, so just double check that everything has an octet. Our oxygen only has 2 bonds, so it needs 2 sets of lone pairs to complete its octet, and the nitrogen only has 3 bonds, so it needs 1 lone pair to complete its octet. The carbons all have octets, they all have 4 bonds to them. This molecule does follow our rules. It follows our rules of atoms where nitrogen wants to have 3 bonds and a lone pair, and oxygen wants to have 2 bonds and 2 lone pairs, and carbon has no lone pairs and 4 bonds. So it does follow those rules, so you can always use those to back you up on these. Okay, so now that we know where our lone pairs are, we can now determine the geometry. Now I didn't specify the geometry, so let's do both. Let's do electron domain and the molecular geometry, okay, just to get the practice in. So let's go left to right. Let's do the oxygen first. Our oxygen, for the electron domain, it has 1, 2, 3, 4 domains. So if it has 4 domains, that would be tetrahedral. For the molecular, well, it has lone pairs, so we know that the geometries are not going to be the same. If I have 2 bonds and 2 lone pairs on a tetrahedral structure, this is going to be bent, which we can see because if I try to connect these bonds, they make a bent structure. Okay, it's a bent line. Okay, next up, let's do carbon. Carbon, for its electron domain, well, it has 1, 2, 3, 4. Yes, there's one hiding in the back there. So it has 4 electron domains, so it is tetrahedral. And since there's no lone pairs, the molecular geometry is also tetrahedral. The same goes for this carbon. It has 4 bonds, no lone pairs, so the electron domain and the molecular geometry are both tetrahedral. Okay, they're the same for each carbon. And finally, for the nitrogen, so for electron domains, it has 1, 2, 3, 4. 4 electron domains. Again, tetrahedral. But since there's a lone pair on there, our molecular geometry is going to be different. So 3 bonds, 1 lone pair is trigonal, pyramidal. Okay, so keep using that chart. If you know how to use it, you'll find it very useful for your exams. Okay, now I want to start putting this all together. So we're going to take what we learned in our past few chapters and we're going to put it all together. So first, what we're going to do in this example is draw the Lewis structure for each of the molecules below and then name them. Name each of them using our rules for naming covalent compounds. These are all covalent compounds because Lewis structures show bonds. Bonds are between nonmetals. Okay, so that's a covalent compound. Okay, so these are covalent compound naming rules. So we want to draw the Lewis structures and then the compound name. So pause your video now and do that. Okay, for time purposes, I'm just going to draw the Lewis structures so that you can check your own work for Lewis structures. If your Lewis structure doesn't match mine, please make sure you're checking your Lewis structure rules to make sure you followed them accordingly. So SiCl4 looks like this. We're going to pretend that there's lone pairs on those chlorines that I'm just not going to draw today for time purposes. Okay, we have AsF3. There's a lone pair on that arsenic there. Finally, we have PCl5. And you'll notice I try to draw these in a way that gives me a hint towards their structure. Again, if you're not that great of an artist, it doesn't have to work out that way as long as you're able to determine your number of electron domains, whether they're bonds or lone pairs, and you know where they are. That's all that matters. Okay, so let's name these. So we have silicon, tetrachloride. So remember, if it's the first one and there's only one of them, we don't use mono. So it's silicon, we name it as is. Our next one we're going to name but add IDE to the end. So that would be chloride. And then to the front we add the number. There's 4 of them, so that would be tetra. Remember, we use the Greek prefixes, so tetra, not quad. So tetrachloride. Here we have arsenic, trifluoride. Tri meaning 3, adding the IDE to the fluorine ending. So instead of fluorine, it's fluoride, arsenic trifluoride. And finally, we have phosphorus, pentachloride. Okay. Let's try another one. For each of the molecules, draw their Lewis structure and identify their number of electron domains and their electron domain geometries. So I give you the names. You're going to have to use the names to determine the formulas so you can draw the proper Lewis structure, okay? And then determine their domains and their geometry. Remember, we don't know lone pairs from our formula, so we have to write the formula first, count our electrons, and then determine if there's lone pairs on anything. So go ahead and pause your video, draw out these Lewis structures, and determine their domains and their geometries. Okay, again, I'm just going to draw the Lewis structures pretty quickly here. If your structure doesn't match mine, just double check you're following the rules correctly. So we have carbon tetrafluoride, that's going to be CCl4. So that's going to be carbon in the center, chlorines all around. I'm not going to show my lone pairs on my halogens right now just for time. We have sulfur trioxide, which is going to be SO3. So this is going to be S. I'm going to draw this in a way that looks like our geometry. Okay, and if you remember, in order to get my sulfur to have an octet, I'm going to take one of my lone pairs from my oxygen and move it down. Okay, so I'm going to just show that as a double bond to my oxygen, and then there's 2 lone pairs there. Okay, so it's sulfur trioxide. Then we have sulfur hexafluoride, that's SF6. So we have SFF. Again, I'm trying to draw this in a way that kind of looks like our geometry, not being very fancy in my artistry. So that's SF6. That's one of our expanded octets. So let's look at electron domains. Chlorine has 4 bonds, no lone pairs, so that's 4 electron domains. Sulfur trioxide has 3 sets of bonds and no lone pairs, so that's 3 electron domains. And then sulfur hexafluoride has 6 domains because it has 6 bonds. So for electron domain, 4 electron domains is tetrahedral. We've done that a lot this lesson. 3 electron domains is trigonal planar. Okay, and then our final one for 6 electron domains, that's our big one, that's octahedral. Okay, so that's it for our lesson today on molecular structure. So before you move on to your next lesson, please make sure that you do your ALEKS homework and make sure you are mastering determining these structures and these geometries so that when we use it in our future lessons, you are prepared.